Hello, my name is Max McMurray, and this is my Lab 1 for Physics 2212. The purpose of this lab is to determine the excess charge in a piece of charged tape. What we're going to use is two pieces of tape, two notebooks, as well as a ruler to measure our distance. The fundamental principles we're going to use is Coulomb's law to find the force of the electric field. And this is equal to the constant K, which is 4 over pi epsilon naught, also equal to 9 times 10 to the ninth, times the charges of both objects being observed over the magnitude of the distance between those two charges and times the unit vector. We're also using the force of an electric field. The force of an electric field is equal to the charge times the electric field. We also use Newton's second law, or the force of gravity, at least the simplistic version of it, which is the force of gravity times mass times gravity. And finally, we're going to use Newton's third law. The electric force is equal to the negative gravitational force, or their magnitudes are the same. Some assumptions we're going to make is that each piece of tape is a single point in space, or point charges, which will allow us to use Coulomb's law. We're also assuming that air resistance is negligible, and both U-tapes, as I will describe later, have the same net charge, or they're charged evenly. So the procedure, you can see a little photo of how part of my procedure on the right side. What we're going to do is we're going to create two pieces of tape with handles. One of them is going to be the base tape, which is going to be placed on a desk, and the other is our quote-unquote U-tape. What we do is we attach this U-tape to the base tape and then rip it off quickly to give the tape a negative charge. We know it's a negative charge because we test it by comparing it with a positively charged pen, and they appear to attract. We create then two more U-tapes, we charge both of these using the base tape. One of these tapes is going to be attached to two notebooks, so the middle is hanging in the air, as we can see in my photo. And using my hands, I'm going to slowly move the other tape up towards the hanging U-tape until the hanging U-tape begins to lift. We're going to then record the distance between the two tapes and then calculate our answers from there. So the measurements that I created, you can see my little calculations that I made on the right side. I determined the length of the tape to be 0.2 meters. I also found the mass of the tape and the distance between the tapes when the floating begins. The magnitude of gravitational force on the floating tape can be found by just using Newton's second law, or the force is equal to m times g, which gives us 0.00196 newtons. This is the same as the magnitude of the electric force on the tape due to Newton's third law. And then using some calculations, I was able to find the electric charge on the tape. This is going to be equal to the mass times the distance between the two squared over Newton's constant, or Coulomb's constant, or K. This will give us 3.556 times 10 to the negative 8th coulombs. Some more measurements that I continued to do were to find the number of atoms in the tape, as well as the ratio of excess electrons. So the area of the tape is 0.2 meters long and 0.09 meters wide, which gives us an area of 0.0038 meters squared. This gives us the numbers of atoms in the tape by saying that the length of an atom is 1 times 10 to the negative 10th meters, which we square then to give us 2.362 times 10 to the 18th atoms in one strip of tape. And then we can divide this by the number of excess electrons we found in the previous slide to be 8.446 times 10 to the negative 8th excess electrons per atom. So this is my code for part 1. Basically what I did is just took everything from my calculations in the previous two slides and put these onto paper. The main thing you need to realize is that my charge of Q is equal to the square root of the force times gravity times the distance, or r vector, squared to give us the magnitude, divided by our constant K, OOFPEZ. The one thing you should notice on here is that the blue ball on the top, which represents our top tape, is our system, so therefore it's undergoing both the electric force of the bottom red ball, which is our bottom tape, as well as the force of gravity pointing down, where our surroundings, which is the red ball, is only undergoing the force of gravity. Part 2 then, basically is an extended model of what I did in the first part. We take our charges and our tapes and basically stretch this out into a line format, where we now have a number of charges, as much as we would like, determined by n over a line, and then we can see these green arrows representing the electric force pulled out into, or stretching out from, the center of our forces. So what if the signs of the tape's charges were reversed? One thing that would happen is there would be a change in the electric field, or the direction they point would invert. As we know that a positive charge points outward and a negative charge points inward, these would flip-flop. However, though, because the magnitude would be unchanged from these, the interactions would remain the same, and what we notice in real life would not be any different. And then why were my Q values different in two models? As we can see, the electric force in part 1 was way greater than the electric force in part 2 of my code. This is because part 1 assumes that all charges were at a single point rather than multiple points along the line, which is what part 2 of my code represents. And that's it. Thank you very much.